All right, boys and girls, this is assignment 4C. This is going to be our introduction to implicit differentiation. I kind of brought up implicit differentiation in the last lesson, but I really kind of didn't explain myself very super duper well. And here's the idea. Typically, when we take a derivative of something, all right, something like that, for instance, we take dy dx, and that means we are taking the derivative of this thing, and we're really focusing on the x's. And so the x's are make the process easier. Okay, but technically that's not the only thing we're taking the derivative of in this case. We're technically taking the derivative of every letter that is in this problem. All right, and so I'll teach you the tricks, and then we'll come back to the better understanding. What would happen if I wanted to take the derivative of x squared plus y squared is equal to 9? That's the equation of a circle. What's the derivative of that? Okay. Now, when both x's and y's are written into the same equation, it makes things way more difficult. And so this is where we want to start to learn how to do implicit differentiation. Implicit differentiation is, in essence, allowing you to do derivatives of every letter at once. All right? So if I want to ultimately understand what the heck is dy dx in this problem, what the special letter is x. So what you get to do is you get to treat x like you normally would in every single problem. So x squared is 2x upon the derivative. All right, now plus. Now where I'm at on the problem is this y squared. And so what I do when I come to a different letter that is not that bottom with respect to letter, okay, if it's not that bottom letter, you still take the derivative just like you normally would as if it were an x. So for instance, I'm going to treat this y just as if it were an x. So that's a 2x, or excuse me, as you were, 2y. I treat it just like as if it were an x. I take a derivative just normally. However, if you are taking a derivative of a letter, like we are here, that is not that bottom letter, then what you do is, okay, I just took a derivative of y. I have to attach this dy dx onto that derivative. If you take that derivative right then and there, you attach this dy dx label to it. Okay? And again, the derivative of 9 is 0. Okay? So that gets the ball rolling with implicit differentiation. Is if you ever take a derivative and it's not the letter that's in question, all you do is you add this like dy dx kind of thing to it. So let me broaden our scope here just a little bit. What is, I ultimately want to know what is dx, what is it? So with respect to x of, let's go 2x to the third plus 7a plus 2b squared is equal to 4x plus c. Okay. So again, the bottom letter that is important is x. All right. So if we take a derivative of an x, cool, we just treat it like normal. However, any other letter, you have to have like that letter, dA dx, dB dx, if you take the derivative at that moment. So this is going to be 6x squared. Or 7a. So it does have the letter a, and so I take the derivative of that a. So derivative of a is 1, so that's 7. But because I just took the derivative of the a, this gets a dA dx. Next bit, okay, I'm still taking the derivative. This is 4b, just like I normally would. However, because it was a b, this is going to be dB dx. And you still continue on to the answer. 4x is 4. Okay, because technically that would be dx dx, which is 1. And then the derivative of c is 1, so that's 1 dc dx. Okay, that is implicit differentiation. Now, obviously, the problems are going to usually stick to x's and y's, and you don't have to branch off into all these different derivatives, but it is absolutely possible. All right. That kind of gets us going, and then I'll teach you the rest of it as we kind of go along here. So you get the idea of implicit differentiation, and then we can work it out from here. So examples are the key to success. All right, so we're looking for dy dx by implicit differentiation. So here we go. So dx is what we're after, dx. And so this is going to be 2x plus 2y, but because that was a y, that was a dy dx, is equal to 0. The derivative of 9 is equal to 0. Okay. I'm going to come back to this problem. And I'm going to do the first step of a lot of these different problems. All right? So we'll come back. We're not done here. We're done here, but we'll come back. So this next one is 1/2 x to the negative 1/2 plus 1/2 y to the negative 1/2. But because I just took that of a y, that's dy dx, is equal to 16. Or excuse me, not 16. Derivative of 16 is 0. Sorry. So you take the derivative of the x, the y, and the 16. Okay, number 5. Okay, we have the x to the third, which is 3x squared minus. All right, here you got to think of this as being the product rule. So minus. And I'm going to create a big parentheses. Okay, and now I have to do the product rule. So the first one is the u prime, which is the x. So that just leaves a regular y plus leave the first alone, and now I take the derivative of the v, which is the y. So y prime is 1, and that gets a dy dx. Because that's where I took the derivative of y. Plus the 2y is going to be 2y, y squared is 2y dy dx is equal to 0. I'll take one more, and then I'll start explaining myself a little bit better. All right, so again, this is a u times a v, so the u prime is 3x squared, y to the third, plus, okay, leave the first bit alone, 3y squared dy dx, minus y, which is now 1, dy dx, is equal to x, which is 1. So whenever you take the derivative of a y, put a dy dx when you take the derivative of a y. If you're not taking the derivative of the y, then just leave it alone. Like, for instance, there. I didn't take the derivative of the y there, so I don't put a dy dx. That's when I took the derivative of the y. So that part gets the dy dx. Okay, now, ultimately, though, what they want is, what is dy dx? Okay, what is dy dx? All right, so the first thing that you do in these problems, let me use this green one as an example. 3x squared minus y minus x dy dx, because the parentheses, plus 2y dy dx is equal to 0. All right. The first thing that you do when you're doing this is just kind of getting all the dy dx's together. So what I do is make sure all dy dx's are on one side, and then everything else goes to the other. And this is pretty much a plus minus kind of operation. So I'm going to save this x dy dx, and I'm going to save this 2y dy dx. But I'm going to move the 3x squared, and I'm also going to move the y. So that will be a minus 3x squared and a plus y. So get all the dy dx's on one side, everything else to the other. From there, what you in essence do is you factor out the dy dx. So it's just like a variable. So dy dx, that leaves a negative x plus a 2y. So I isolate the dy, I get all the dy dx's on one side, I factor it out, and then I divide off the parentheses stuff. So dy dx, and I divide off the negative x plus 2y. So this is negative 3x squared plus y all over negative x plus 2y. And there's your derivative. Okay, there's nothing multiplying into this, so I really don't have to worry about it. So again, I'm going to save all the dy dx's. So that would be this 3x to the third y squared, and this minus 1. And then I'm going to move everything else. So that would be the 3x to the third, y to the third. So I kept all dy dx's on one side, and then moved everything else to the other. The 1 was already over there, so be it. All right, I factor out the dy dx. That'll leave a 3x to the third y squared minus 1. And then I divide that off. So dy dx, I'm going to move the equal sign. I hate moving the equal sign, but so this is 1 minus 3x to the third, y to the third, and I divided off 3x to the third, y squared minus 1. And that's what dy dx is. So you're not making it into an equation with x's or anything like that. You're doing it implicitly, and then you're just isolating the dy dx. So let's go back to the easier problems. All right. So here, the only dy dx to save is the only one with the dy dx, and so that will push the negative 2x over. Okay, so isolate it, which it is, and then divide off what you don't want. So dy dx is equal to negative 2x over 2y, aka negative x over y. All right, so here we have 2 square root y 1 dy dx. I'll save that, and I'll push everything else. So that's going to be minus 2 square root x over 1. So that's a minus. And then I divide what I don't want. Now, when I divide something that is already on the bottom, it goes to the top. So this would be a 2 square root y on top of a negative that is already there. to square root x. So this is what? Negative root y over root x. Negative root y over root x. Okay. Back to the harder problems. Here we have a u and a v, so a derivative of x is 1 plus the derivative of the second bit is e to the y. So e to the y is e to the y. I didn't take a derivative of y there. Or did I? Yeah, well, kind of. And then the chain rule would be on the y, so that gets the dy dx. Minus 10x, so that'd be 10, plus 3y, so that's 3 dy dx. It's already equal to 0, so no big deal. So save the dy dx's, so dy dx's, and I'll kind of skip a step here. So that's an x e to the y and a plus 3. All right, so again, the bits that I'm saving is this and this. I'm moving everything else, so that's a negative e to the y and a positive 10. Divided off, dy dx is equal to negative e to the y plus 10 over x e to the y plus 3. Here you go. Sine goes to cosine, so cosine x, derivative of x is 1 plus cosine goes to negative sine. So negative 2 sine 2y, derivative of the inside chain rule. Okay, so I didn't take the derivative of y right there. I was taking the derivative of the cosine portion. Okay, so but the chain rule is I have to chain rule this inside. So that's 2 dy dx. And then the derivative of 1 is 0 as the answer. So dy dx is saving what? Negative 4 sine 2y. That's going to be equal to negative cosine. Parentheses. Divide off what I don't want. And negative is going to cancel. Again, I hate that I'm moving parentheses. I wouldn't do this if I were doing this on my own picture, on my own paper. Try to line up your equal signs. All right, here we go. Derivative time. What color haven't I used in a while? Blue. Sine goes to cosine. X goes to 1, so no big deal. X is 1. Plus, leave the first bit alone. Derivative of the second is the 1 plus tangent. 1 plus tangent is 1 goes to tangent goes to secant squared. Derivative of the inside is dy dx. I'm just going to see what I have here real quick. Here I have a cosine x and a 1 plus tangent y. I'm just trying to get rid of as many parentheses as I possibly can. Plus, this is an x secant squared y dy dx. Just trying to get rid of parentheses. So keep the dy dx, move everything else. So that'd be a cosine minus 1 minus tangent. All right, so that saved it, and then everything else would be over there. And so that is an x secant squared y. And then so I divide that out. I'm sure I'm breaking some like trigonometric law about the order in which you write stuff. But I really don't care right now, so I know I have the right answer. But, and again, like things like are making my spidey senses go crazy, like having a secant in the denominator, it's weird. You might as well just put a cosine squared up top. But then I'd have to multiply it with a bunch of other stuff. Yeah, so I'm not really concerned about it. But yeah. So this answer could probably very well look 1,000 different ways. All right, here we go. So the derivative of y is 1, so that's dy dx. Derivative of sine is cosine. Let me change colors. Go green. Okay, again, derivative of y is 1, but that was a y, so dy dx. Derivative of sine is cosine. Chain rule of the inside would be times, chain rule is the x leaves y, plus the first part derivative of y is dy dx. Okay, so that's the chain rule. This y plus x. Get all dy dx to one side. I'll move those all to the left. So 1 minus x cosine xy. That's the stuff that had the dy dx. And I'm left with y cosine xy. Divide off what I don't want. If you weren't a big fan of the chain rule before, you may want to get on board. The x squared minus 1 over y dy dx plus 2y dy dx is equal to 0. So this is a what, a negative 3 over y, or 3 plus 2y to negative 2x. One quick cleanup. Such, then divide. Just basically divide. So dy dx equal to negative 2x y. Bottom comes up and the top goes down. And 4x to the third, that's 12x squared. The ln is 1 over times chain rule plus 2y, y goes to 1, equals 2x, 2x goes to 2. All right, so 2y over y squared is going to be 2 over y. So this is a 2 over y, and then this is a plus 2. And then this side has a 2, and then a minus 12x squared. 2 plus 2y over y. Sure, it's going to make a difference. And then divide or flip the flop. That's going to be y comes up over 2 plus 2y. Like that. Good enough. Good enough. Get GCF out at 2, but get GCF out at 2. Both numerator and denominator canceling, but whatever. What I'm saying is you can GCF out of 2, so this would be 2y, 1 minus 6. And this denominator is 2, 1 plus y. Cancel out of 2. That's what I said. All right, so we're supposed to differentiate this implicitly, and then we're going to evaluate it at a point. Okay, so you'll see what to do. Here we go. So the first is again, this is u times v. So like u is x, v is y. So u prime is 1. V prime, however, is 1, but dy dx. So just kind of think about like what would a u prime v plus a u v prime look like. So u prime v plus u v prime. So this is by like a lot of this stuff kind of x. All right. So that's the breakdown. I like kids historically have a very difficult time with this problem when it comes to implicit differentiation while simultaneously doing the product rule. For some reason, it's just a big old hiccup. All right, so the derivative of x is 1, leave the y alone, plus, leave the first part alone, take the derivative of the second, that's the y. So that's dy dx. Derivative of 6 is 0. Save that, move everything else, so dy dx is negative 1y, and then divide. All right, so that's our derivative. That's dy dx. Now they want to know what is the derivative when we have the point negative 6, 1. So they give us an x and also a y to use. So how this will kind of look is this is dy dx. You may have seen me write this big vertical line. That means I'm evaluating the derivative at, and then I write in a little subscript what I'm doing to the problem. So I'm making my x's negative 6, and I'm making my y's negative 1. So this is going to be 1 over negative 6, aka negative 1/6. Okay, so find the slope of the tangent line of the graph at the given point. All right, so u is the x squared plus 4. So that is going to be 2x, leave the second part alone, plus leave the first part alone, derivative of the y, dy dx. And they have factored it for us. Derivative of 8 is 0. Wow, they factored it for us. That was a nice one. So this is what? Negative 2xy. And then divide. So that's the slope, but they specifically want it at 2, 1. So we are going to take this derivative, evaluated at 2, 1. So this numerator is going to be negative 2, 2, 1 over 2 squared plus 4. So this is what, negative 4 over 4 plus 4 is 8. It's negative 1/2. Okay, more derivative. This is a big assignment. 2y minus 3 to the first power times chain rule. There's the derivative. Is equal to 4. So dy dx is going to be equal to 4 over 2y minus 6. I'll just write it like that. And then they wanted it at 6, 1. So dy dx at 6, 1 is 4, 2, 1 minus 6. This is 4 over negative 4, which is negative 1. Derivative 2x, or x squared is 2x, plus, leave the first part alone, derivative of the second, minus 18x, excuse me, as we were minus 8y, 0. So we have 2y minus 8y Jesus. Lost mistake. X squared 2y minus 8y. That is is equal to negative 2xy squared plus 18x. So dy dx is equal to negative 2xy squared plus 18x divided by 2x squared y minus 8y. And you can factor out a 2 of everything. So this is negative xy squared plus 9x over x squared y minus 4y. Cancels. We want this derivative at negative 4 2 root 3. All right. So I'm going to kind of do some math and some writing. So here we go. So negative 4, positive 4. So this is going to be 4. Y squared is going to be 4 times 3. That's y squared plus 9x all over x squared y minus 4y. Dirty math there. I think it's just going to kind of turn out to be a number of some sort. So 4 times 3 is 48 minus 36 all over 32 root 3 minus 8 root 3. So common denominator or common thing there. So that is what 20. 24? 24 root 3 all over 48 minus 36, 12. So this is 1 over 2 root 3.
The gravy.
All right, so find the second derivative, that d squared y dx squared is the second derivative, and that gets really, really fuzzy when we talk about implicit differentiation. Anyways, 2y dy dx is equal to 3x squared. Okay, so dy dx is equal to 3x squared over 2y. Okay, that's the first derivative. This is where it gets crazy. So taking the second derivative of this, I'm taking the derivative of this derivative. So d squared y dx squared is the derivative of the left-hand side, and now the right-hand side is bottoms up. Derivative of the top minus, leave the top alone. Derivative of the bottom all over the bottom squared. Okay, so here's where it gets a little fuzzy. So we've taken the second derivative and everything implicitly, but now what we need to do is we need to replace that dy dx with what dy dx really is, right? So we need to use that first derivative in there. So this is a 12xy minus 6x squared, and here's where it gets crazy. This is a 3x squared over 2y, all over 2y squared. So again, I knew what dy dx is from the original derivative, so you have to take it out and put in what the derivative is. So I took that derivative, the original derivative, and put it in there. Now I created another problem for myself, though, and I have, in essence, two fractions inside of a fraction. All right, so this side is going to have a 2y to get a common denominator. So this is going to be what, 24xy squared minus 18x squared, excuse me, x to the fourth, all over 2y. And then, so this is all over 2y now. And then this 2y squared is going to multiply up into the denominator. That's what they do. One goes to the top and 2y. So this will be over a grand 2y to the third. You can take out a 2, but yeah, you can take out a 2. So 12xy squared minus 9x to the fourth. This is actually 8y to the third, so this is going to be 4y to the third. Again, the denominator is the same thing, 8y to the third. I don't really know what logarithmic differentiation is. So I don't really know what logarithmic differentiation is. No idea. Here it is. So this is x leaving x squared plus 1 to the 1/2 plus. Okay, I see the trick. And I think I kind of taught you this guy before. This is the same thing as saying an x squared on the inside. So this is going to be x to the fourth plus x squared. I think that's the idea of like logarithmic differentiation, maybe. Same kind of idea. So the derivative is 1/2 x to the fourth plus x squared negative 1/2 times 4x to the third plus 2x. So this is going to be divided by 2. It's going to be divided by 2. And so this is going to be square root, and so this would be x squared plus 1 all over 2x to the third plus 1. Okay, again, this is x squared, because this is ultimately a square root. So y is equal to, be careful, dude. E y dx, this is just nasty. Bottoms up. Derivative of the top. This is x plus 1 to the 1/2. All right, I'm just going to stop there. This is stupid. This is stupid. Stupid. I think you can square that. And then on this multiplication, it'll become to a normal x plus 1. But then you have to bring it in here, so that'd be another normal, or that'd be an x plus 1 squared, and the second one would be an x plus 1, or x minus 1. No, that's an x plus 1. No, I can't multiply anything like that. Well, I can, but it's an x plus 1 versus an x minus 1, not the same thing. Yeah. Again, I don't know logarithmic differentiation, but the reason that I don't know logarithmic differentiation is because I never had to use logarithmic differentiation. It's like, unless this is the first time in umpteen years that it's going to be on the test, I'm not worried about it. I am not worried about it at all. Slope of the tangent. Okay, we can do this. All right. So the derivative. Okay, when you do this, do the product rule inside its own parentheses, because that produces a plus, which is actually technically a minus. Okay, so again, this minus comes in, and so just be conscientious of that. All right, so they have this derivative, but they want the derivative at 1, 1. So this is -4 plus 2 over -1 plus 4. Okay, second derivative at 6, 8. So 2x plus 2y dy dx is equal to 0. So dy dx 2y -2x, divide by 2y and simplify, that is going to be -x over y. But they want the second derivative. Okay, so here comes the second derivative time. So d squared y dx squared. So bottoms up, derivative of the top, plus leave the top alone, derivative of the bottom, all over bottom squared. And so this is going to be negative y minus x dy dx, which is negative, a little bit closer. So this is negative y over x all over y squared. Cleanup time. This is going to have a denominator of x, so I'm going to put an x on that side. And now everything has a denominator of x. Negative times negative right there. So this is going to be negative xy plus xy all over xy squared, which is 0 over xy squared. So this is going to be 0, but what did I do wrong? So I asked the ether. Bottoms up, derivative of top, leave the top alone, derivative of bottom squared. Is negative x over y. Jesus. Here it is. Negative x over y. So as I was saying, this side needs a y. All right, now it has a common denominator. And so this is going to be negative y squared minus x squared. Oh, I smell a super trick here. Over y to the third. And here's a trick that a lot of times, just because I've done enough of these problems, that I think it's silly that they have these anymore. But you can go as far back as, you know that x squared plus y squared is equal to 100. Okay, so that's the second derivative in itself. And then what is dy dx? That's 6, 8. And so that'd be negative 100 over 8 to the third, whatever that is. 5 1/28. Oh, negative. I'm sorry, negative 100. Negative. Which points of the graph of the equation have a vertical tangent line? Which points of the graph have a vertical tangent line? So whenever y is equal to 1. Okay, so vertical tangents are where the denominator is equal to 0. So that implies vertical tangents is, in this case, where y is equal to 1. That would make my derivative of my tangent equal to 0. That's a vertical tangent. So what points of the equation have a vertical tangent line? And that's whenever y is equal to 1. Y is equal to 1. I'll just leave it like that. Unless, I'm just going to plug in chunk here real quick. X squared plus 4 plus 6x minus 8 plus 9 is equal to 0. That's the original equation. And so x squared plus 6x plus 5 is equal to 0. And then that would be x plus 1, x plus 5. And that would mean -1 and -5. So the points would be -1, 1, and -1, -5. Those are the points of the function that have a vertical tangent line. Horizontal tangent line is when the derivative is equal to 0. And so that would imply when -x plus 3 is equal to 0, and that would make x equal to 3. So whenever x is equal to 3, that has a horizontal tangent line. So again, doing the same trick, going back to the original, this is what, 9 plus 4y squared plus 18 minus 8y plus 9 is equal to 0. So 4y squared minus 8y plus 36 is equal to 0. 4y squared minus 2y plus 9 is equal to 0. Gross. Y squared minus 2y is equal to -9. Y minus 1 squared, and then plus 1 plus 1 is equal to -8. No, so this is never going to happen. Never going to happen. Because this would be y minus 1 is equal to plus or minus square root of -8. Yeah, that just doesn't happen. I probably did bad math right there. I probably got that answer wrong. But I've been at this so long that I really don't mind. You can go back and fix it yourself. All right. So, yep, that's it. I gotta go to golf practice.